When modern companies make critical decisions based on static totals or historical averages, they are operating on a dangerous illusion. To optimize production, businesses don't look at the average, they look at the margin, the exact cost, revenue, or output generated by producing precisely one additional unit. Isolating the exact value of that single theoretical next unit requires mathematical tools far beyond standard arithmetic. If economic growth and costs scaled at a constant, perfectly linear rate, basic algebra would be enough to find that value. In reality, businesses deal with compounding costs, fluctuating demand, and shifting efficiencies. Growth is almost never a straight line. Therefore, to optimize effectively, we need a mathematical system built specifically to measure constant, unpredictable change. This diagram plots a simple, straight linear trend. Traditionally, we find the slope of this straight line using basic algebra, calculating the change in y divided by the change in x. This calculation works perfectly for constant rates of change, where the slope is identical everywhere. But real-world costs and revenues form complex, nonlinear curves. If we apply that same algebraic bracket here, it fails. The slope constantly changes, making wide averages useless. This is where we introduce differentiation, a mathematical process designed to solve this exact geometry problem. Differentiation bypasses those wide algebraic brackets entirely. It allows us to pinpoint the exact rate of change at a single, microscopic point on that curve. Transitioning to differentiation provides the precision needed to measure the margin at any scale of production, regardless of how complex the curve becomes. To find the exact margin on a curve, we must locate what is known as the tangency point. The derivative is simply the specific slope of this tangent line. We denote this derivative as dy over dx. Graphing curves and drawing tangent lines manually for every business decision is incredibly inefficient. So mathematicians use a highly scalable algebraic shortcut. The shortcut is called the power rule. It provides a clean algorithmic method for finding the derivative. First, bring the original exponent down to the front, multiplying it by the base number. Second, subtract 1 from that exponent. There is also a crucial rule regarding standalone numbers. Any constant number without a variable differentiates to exactly 0, because constants do not change. The power rule transforms the highly complex geometric problem of tracing curves into a fast, reliable, and easily repeatable arithmetic algorithm. Let's apply this rule to corporate finance, specifically focusing on finding marginal revenue. Marginal revenue is precisely defined as the derivative of the total revenue function with respect to quantity. Imagine an inverse demand scenario where the price equals 180 minus the quantity produced. To find the margin, we first calculate total revenue by multiplying the price function by quantity, giving us a total revenue equation of 180q minus q squared. Now apply the power rule. For the 180q component, the implied exponent of 1 multiplies the base, then drops to 0, leaving just 180. For the negative q squared component, we bring the 2 down to the front to form negative 2q. This leaves us with the finalized marginal revenue function, MR equals 180 minus 2q. With just 2 brief lines of algebra and calculus, we have successfully extracted the dynamic revenue value of the exact next unit produced. Pivoting from revenue to cost reveals a common analytical trap, confusing average cost with marginal cost. It is a hard mathematical rule that you cannot differentiate an average metric directly into a marginal metric. We must bridge the gap between these metrics. We always convert the average into a total before applying any calculus. Consider a complex scenario where our average cost equals 100 over q plus 4 plus q. To bridge this, we multiply the entire average cost equation by quantity to isolate total cost. This transforms our equation into 100 plus 4q plus q squared. Now we execute a power rule sweep across the total cost equation to find the derivative. The constant 100 drops to 0, 4q becomes 4, and q squared becomes 2q. This gives us the finalized marginal cost equation, 4 plus 2q. By bridging averages through totals, differentiation uncovers the true marginal cost. This is the only metric that accurately dictates whether a firm should scale up or scale back production. This mathematical framework extends beyond financial numbers into physical production, specifically measuring the marginal product of labor. The marginal product of labor is the extra physical output gained by hiring exactly one more worker. A firm's production function, quantity equals 300L to the power of 0.5 minus 4L. Differentiating with respect to labor yields our marginal product of labor, 150L to the negative 0.5 minus 4. Note the negative fractional exponent on the labor variable. With a negative exponent, as the labor pool increases, the term's value mathematically decreases. This connects to the law of diminishing marginal returns. The top graph shows total output flattening, while the bottom graph proves the marginal value of each new worker actively drops. Differentiation provides the fundamental structural logic that links abstract mathematical equations directly to the physical limits and strategic behavior of real-world firms.